Welcome back. Today I'm going to be completing part D of homework 3 for process dynamics and controls. And what we're going to be doing in this first part is we're going to derive the Laplace transform of a time-shifted function with dead time theta. And to just initially explain kind of what dead time is, if we were looking at a time-dependent function, f of t, that looks something like this. Our shifted function with our dead time, time-shifted function, would be the exact same with this gap in between. And this gap is our dead time. Which you can see probably in a lot of like real systems when we're talking about you have a signal going to your controller, just natural physics could result in the signal being received to the controller's action. For example, that would be an example of dead time. And this is what it looks like for a function graphically. And it's going to kind of aid us in how we're going to perform this Laplace transform. So to do this, we need to account for this dead time in our function. And to do that, we're going to say that our f of t minus theta ut minus theta is our time-dependent function with dead time accounted for. And in order to take the Laplace transform of our function t minus theta u t minus theta, we're going to need to say that it's equal to the integral from 0 to infinity of our function of t minus theta u t minus theta times e to the minus s t dt. And to simplify this down a little bit farther, we can say introduce our variable tau, which is going to be equal to our t minus theta that appears in our function a lot. And then inversely, we can say that t is going to equal tau plus theta. So summing this into our equation, we get that the Laplace transform is equal to the integral from minus theta to infinity of our f of tau u tau e to the minus s times tau plus theta d tau. We can simplify this further in two ways. We can say that our e to the minus s theta is not changing with this integral, so we can move that out front. And then we can also say that our minus theta is also equal to 0, because that's where we're starting at. We're starting at our 0, so our minus theta is 0. So our integral is from 0 to infinity, not from minus theta to infinity. So we can say e to the minus st. What am I talking about? E to the minus s theta times the integral from 0 to infinity of f tau u tau e to the minus s tau d tau. That's our function we're looking at. And now that we've got it into this form, we can sub this out with our Laplace function. So we can finally say that the Laplace transform of our time-shifted function f t minus tau u t minus tau is going to equal our e to the minus s theta times our Laplace big F of s. And that is the Laplace transform of a time-shifted function with dead time theta. So we're good to go ahead and move into the next part. Now that we know how to perform a Laplace transform on a system with a function that has dead time, we can apply this so that we can find the transfer function for a Ziegler-Nichols closed-loop proportional integral controller. There's going to be a couple changes from our proportional only controller functions, but to get us started, I'm going to kind of draw out our closed loop again, our visual representation of our closed loop with the GC on the controller, our process, our GP, and then our GM, our measurement device. So if we remember previously, we said that our GC just equaled KC for our proportional controller, proportional only controller. But now that we have this integral element, we're gonna have to account for that by adding this 1 plus 1 over tau IS. And that is going to be our integral controller GC. And then for our GP, it's kind of an obtuse G. For our GP, we remember the general function r k over tau s plus 1. And in order to bring this into the proportional integral control with a dead time, we can apply this general form we found earlier to this, and we can say we know that this is our f of s, our Laplace domain function of s. So we can simply multiply this by r e to the s theta, and say GP is going to equal for this controller k over tau s plus 1 times e to the minus s theta. And that is going to be our function for our process on our proportional integral closed loop. And then finally our GM, we're going to keep that the same as we did before. We're just going to say that GM just equals 1 for our purposes today. And then, as we did before, we're going to combine all of these into our G-closed, our overall function, which, if we remember, is GP times GC all over 1 plus GP GC GM. But instead, what we had before, we're going to use these new transfer functions for our proportional integral controller. So now we are good to go ahead and move into Python and simulate an example of this Ziegler-Nichols closed-loop proportional integral controller and get a little bit of a plot together to see how this is going to look. So let's go ahead and move over into Python.
All right. Now that we're back, you wouldn't believe it. I actually recorded this entire video already, but yet again, my headset cut out. But this time I'm just going to completely redo it. So what I've got set up here is the entire problem, because I had all of the coding work that I just did in there, but I had to delete it because the mic wasn't working. But I believe that we should be working now. All right. Well, let's get right back into it. So, as we were talking about up on the board, we figured out our Ziegler-Nichols transfer functions up on the board, our GP and our GC, and then our overall closed loop transfer function. But what we're going to need to do is use these Ziegler-Nichols empirical constants they have here and apply that to our closed loop method. So to get started here, in class we determined an ultimate controller gain of around 17.85. So I'm going to stick that in there, and then a tau u of 0.35 as up in here. We're going to use these values to then multiply by these Ziegler-Nichols empirical values they have up here. So we're going to say that our Kc is going to equal 0.45 times our Kcu up above, and then we're going to say that our tau I is going to equal, where is it, 0.83 times our Tu. Fantastic. Now that we have those in, we can go ahead and put our problem values in. So we know that our K is going to equal 1 from up above. Our tau is also going to equal 1, and then our dead time theta is going to equal 0.1 seconds. So now we have those values in there. We can go ahead and put in our GP and our GC. So we know that our GP is going to equal, what I have up here, our K times 1 over our tau times S plus 1 from that equation we found up on the board there. What am I doing? And that is our GP. And then our GC, as we said up on the board, to get our integral portion, we're going to have our Kc times our 1 plus 1 over tau I times S. I believe, yep, that's perfect. And there's our GC. And then we can find our G closed, which, as per usual, is just going to be our GP times our GC, all divided by 1 plus our GP times our GC. Bang, there's our G closed. And now that we have that, yet again, we can run a simulation. So we've got our T and our H, even though this particular problem, we're not actually looking at like tank height or anything. They're familiar variables, so we're going to stick to T and H for now. So we're going to say T and H equals sim of our G closed, the lambda times step of 1, n equals 1,000, and then our dt is going to equal 0.01, so we're not looking all choppy. That all looks good. Going on from there, I think we're good to go ahead and make our plot. So we can say fig equals make subplots. We can do fig dot add scatter. We're going to have our x equal to our t as usual, our y equal to our h, and our mode is going to be lines. Let's see how that looks. All right, what's going on here? S is not defined. Shouldn't be a problem, right? I see I forgot to put in the most important part, our e to the power of our negative theta times our s. I'm pretty sure this will fix everything. Shift enter. Why are we complaining about the s now? I found the problem. I forgot to run our CHE tools, so that's why this whole thing was freaking out a little bit. Beautiful. Look at that. We got our dead time down here before our process starts, as we talked about up on the board. Then we got a big old jump. We go a little bit over our set point, dip down, but then we hit our set point and we stay there after just a little bit of overshoot and a little dip in there. But now that we've done our Ziegler-Nichols method, we can move on to our Smith-Caripio method, which is more of an empirical method that's going to allow us to not overshoot as much as we do with the Ziegler-Nichols method. So as you can see here, I went ahead and copied over our page from our textbook that has our P and I values for A and B, our empirical values for our constants. That was provided in the Canvas announcement, and we're going to apply that to the Smith-Caripio open loop constants. So let's go ahead and get to that. So we know our PA and PB are going to equal that 0.586 and the negative 0.916. And then we know IA and IB are going to be 1.03 and negative 0.165. Cool. And then once we have those, we can go ahead and find our big Y, which we're going to use to calculate some of the other relevant constants later on. And our big Y is going to be our PA times our theta over our tau to the power of our PB. And then we can find our Kc to be our Y divided by our K. And then finally, we can find our tau I to be our tau divided by our IA plus our IB times our theta over tau. And that's how the Smith-Caripio method uses these empirical values to find those constants that we had found with the Ziegler method up above. And now that we have those values, a lot of the rest of the stuff we can just copy down from up here in the Ziegler-Nichols method, as our GC, GP, and Gclose all stay the same. Go ahead and copy those down. And then same with our simulation and our plot making lines. So if we take a look at this, we can see that the Smith-Caripio empirical method manages to hit that set point with very, very little overshoot. If we examine this little thing, we just barely go over, and then we hit 1, making this method seemingly a lot better for, I don't know how to get to the original auto scale. There we go. Making it a lot better for systems where you wouldn't want a ton of overshoot, versus the Ziegler-Nichols methods where you're definitely going to have that big overshoot, but then you will steady out at your set point. So I believe that is the end of homework 3, part D. I will see you guys in the next one for separations.